All right, today, guys, we're going to be talking about polar equations, section 6.4. So let me show you our notes. So here are the notes that are out on Canvas for you. It says polar equations. So it's a polar equation is an equation that is using r and theta. So it was just like we were doing the last section where we were graphing coordinates with r and theta. And we were using graph paper that looked like this as opposed to our standard Cartesian coordinate plane. So all of our equations are going to be in the form of r equals a cosine theta or r equals a sine theta, where a is a positive number. So I gave you two examples here. R equals a cosine theta is a circle that is symmetric about the polar axis, and r equals sine theta is a circle that is symmetric about the pi over 2 axis. So what I want to show you before we get started is what you can do with your calculator. So in your calculator, if you go to the mode button and the fourth item down says function, parametric, pole, we want to choose polar equations, and we want to make sure that we're in radian mode. So now if you notice in your window, our window has a theta max and a theta min, and it has an x min and an x max and a y min and a y max. So I've set my x min and x max to be 0 to 2 pi. I don't remember what I put my step at. It doesn't really matter. And my x min, I set at -5 and 5, and my y min, -5 and 5. So when you go to your equations now, you'll notice that when you type in an equation, it says r instead of x on this left-hand side. And if I type in this first equation for sine theta, notice that theta is coming up instead of x. So when I graph that, let me turn this graph off. When I graph this, what I end up with is a circle. It's a little distorted because of my screen. But also notice that when I change my equation from sine to cosine, now my graph is symmetric about the x-axis or the polar axis. So that's something you can do in your calculator to check things out. So how are we getting this equation? So all we're doing is we're taking values of theta on our unit circle, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. We're substituting those into this equation. So sine of 0 is 0, so 4 times 0 is 0. Sine of pi over 6 is 1/2, so 4 times 1/2 comes out to be 2. Pi over 3, we get an equation, but it's 2 square roots of 3, which is about 3.46, and pi over 3. And we can keep doing that with these different points. So then when I go to graph those points on my polar graph, so our first point is 0, 0, so that's right here. That's right here. Our second point is 2 and pi over 6. So that means, remember, we go over 2 and up to pi over 6. Our third point is about 3.46, we're estimating, and pi over 3. So 1, 2, 3.5. And pi over 3 is right here. Our next point is 4 and pi over 2. So we're going up 4 to pi over 2. Our next point is 2 square roots of 3 and 2 pi over 3. So again, that's about 3.5. So 1, 2, 3.5, and 2 pi over 3 is right here. And then 2, 5 pi over 6. Here's 5 pi over 6 and 2. And then 0 and pi is right here. So that's how we're getting that graph that you see on the graphing calculator. Okay. We can do the same thing for other problems, but what we got into here is talking about actually the symmetry of these items. So instead of going into so much detail, what I would like for y'all to understand is that basically any graph that involves cosine is going to be symmetric about the polar axis. So cosine is symmetric about the polar axis. And remember, the polar axis is our x-axis. So this is our polar axis, right? So any problem that involves sine is going to be symmetric about the axis pi over 2. So this is our y-axis or our pi over 2 axis. So if they involve sine, it's going to be symmetric about that axis. So knowing that information, if I have a sine problem, I know that it's going to be symmetric about the pi over 2 axis. And if I have a cosine problem, it's going to be symmetric about the polar axis. So let's go back to this again. So here's our second problem, 1 plus 2 sine theta. Oops. If I go to my calculator, and what I have in here, I'm going to clear these out because I already showed you that. Okay, so what I have in here is 1 plus 2 cosine theta. So knowing that it's cosine, it should be symmetric about the polar axis. But I'm going to change it to sine because that's what we have on our paper. And that means that this one's going to be symmetric about the pi over 2 axis. And if I change the problem to cosine, then now my problem is symmetric about the polar axis. So it's as simple as that. So we're going to go to our next piece of information, and this is also in your notes. And this is the information that is the most important. So what this has are the different types of graphs that you can have with polar graphs. So our first type of graph, these are called limicons. And so we have 4 different types of limicons. So let's see if I can get a little bit closer here so you can see a little bit better. Okay, so what we have here, we have problems that are in the format of A plus B sine theta, A minus B sine theta, A plus B cosine theta, or A minus B cosine theta. A and B are always going to be positive numbers. So the A divided by B ratio determines what the shape's going to look like. So here are our choices. If A divided by B is less than 1, so if A divided by B is a fractional value less than 1, it can't be negative because A and B are both positive numbers. So basically, if A divided by B is between 0 and 1, then we're going to end up with what we call a loop, an inner loop limicon. If A divided by B is equal to 1, then we're going to end up with a heart shape. It's called a cardioid. So we have that little bump on the inside there. So we don't have the loop, we just have that little dimple. Okay, if A over B is between 1 and 2, okay, so it's less than 1, greater than 1 or less than 2, then we have more of a dimple. So this one actually has that little pucker in there, but this one just has a little bit of a dimpling on it. And if we have A over B is greater than or equal to 2, then it's going to be no dimple but no inner loop. So it's almost flat on the side, so it looks just almost like a circle. Okay, so those are our limicon problems. The other options that we have are for graphs where you have something like 2 theta, 3 theta, 4 theta, 5 theta, and we have a value for a here. And again, a is not equal to 0. So for these, for sign problems, remember I told you that sign problems have to be symmetric about the pi/2 axis. So sign problems, you're going to have a problem that looks like this. So notice that when it's 2 theta, I have 4 petals. When it's 3 theta, I have 3 petals. And notice that this is symmetric about the polar axis. When it's 4 theta, I have 1, 2, 3, 4, 5, 6, 7, 8 petals, right? But when it's 5 theta, I have 5 petals. So the pattern is this. If the value is odd, I'll tell you right here, if n is odd, then it has that many petals. So 1, 3, 5, 7, 9 will have 1, 3, 5, 7, or 9 petals. Whoops, petals, right? But if it's 2, 4, 6, 8, if it's even, then it's going to have 4, 8, 12, 16 petals. So it doubles the number of petals, okay? All right, and again, talking about the symmetry. So for example, this one, technically you could say that this is symmetric about the polar axis, but it's also symmetric, I said that wrong. This is symmetric about the pi/2 axis, but it's also symmetric about the polar axis. This one is just symmetric about the polar axis. You notice the symmetry here, and then these two can be flipped. This, it's a cosine, is symmetric about the polar axis. It also is symmetric about the pi/2 axis. This one is symmetric about the pi/2 axis, not symmetric about the polar axis, because I can't flip that down here. So these are called rose petal problems. Rose petal problems do not have anything added in front, so it's not like 1 plus or 1 minus or anything like that. And all of our angle measures are multiples, like 2 theta, 3 theta, 4 theta. So technically, if I go over here, I should erase the 1 because that's not true. Those fall into that category. Whoops, that was a 2. Okay. All right, our last option are problems that are called lemniscates. And lemniscates look like this, and the problems are always in the form r squared equals a squared sine 2 theta. It's always going to be 2 theta or cosine 2 theta. It's never going to be any other multiple of theta. And it's always going to be r squared, and the value for a is always going to be technically the squared. So let's go back for a second. I forgot to talk about a here. So a is representing the length of the petals. A represents the length of these petals. I forgot to tell you that. Same thing here. A represents the length of the petal, right? But this number here is a squared, not a. So I have to take the square root of that to figure out the length of this petal. Cosines are always symmetric about that polar axis, okay? And notice again, this one's technically symmetric here, and it's symmetric here, right? But the sign problems are always symmetric with respect to the origin. So if you think about that, they're symmetric this way. They're not symmetric against the pole, and they're not symmetric against the pi/2. Okay? So this piece of paper, keep it very handy because it's going to be very important. So now when we look at this list of problems and we start talking about what kind of problems they are, right? So remembering our rules. So these first problems here, okay, some of them are limicons and some of them are, all of them are limicons because they all have a single theta value in here. Okay, so these are all limicons. So let's look at that. So in this case, A is 0 and B is 1. So what we're going to end up with is Basically, we're going to have here a circle. Okay. So we already did this problem. Oops. Got some new batteries. So we have 2 cosine theta. And if I graph that, we basically just have a circle. So what we find here is that the length of this circle is 2, or the diameter of this circle is 2. Okay. So 2 sine theta is going to be a limicon that's going to be symmetric about the y-axis. 1 minus sine theta. So A is 1, B is 1. So A divided by B equals 1. Right? So A divided by B is equal to 1. So it's going to be a limicon that looks like this with that heart shape. Okay, they call it a heart shape cardioid. So if we look at that one on our calculator, we have 1 minus sine theta. So what we're going to see, and we might not see it very clearly, is we have this little dimple that's coming in here. Okay, so we have that little bit of a dimple that's coming in there. If I change my window maybe and make it -2 and 2, -2 and 2, and I look at it, there you can see it even better. See the dimple that's coming on the inside. Okay, so again, A divided by B is 1. That falls into this category here, which means we're going to have that dimple or the heart shape. Okay, again, A is 1 and B is 1, so A divided by B is 1. So we're going to end up with a shape that looks like this again. It's a sine problem, so it's going to be symmetric about the pi/2 axis. How's it going to change our graph? It becomes a plus sign. So how does that look different? It's a positive in our positive coordinates as opposed to our negative coordinates. Okay, so 2 plus 2 cosine theta, same thing. A over B equals 1. So again, I'm going to end up with a graph that looks like this. How is it going to look different? Because I put a 2 in front of it. So let's see what happens if I put another equation in here. I'm going to use the same one, 2 plus 2 sine theta. And I'm going to graph it. So how do these look different? Okay, so I need to change my window. I'm going to change this to -5 and 5, -5 and 5. So there's our first one, and there's our second one. So notice that diameter, if we can say the word diameter, is 2 on this one, and the diameter on this one is 4. So the 2 plus 2 is affecting the diameter, okay? Or we can look at it from this perspective. It comes out to 1 here and 1 here. It comes out to 2 on the polar axis here and 2 on the polar axis here. So that gives us some ideas of what we're looking at there. So this one, we have 2 minus sine theta. So 2 divided by 1 is 2. 2 divided by 1 is 2. That means it's equal to 2. So it's going to look like this. It's going to be sort of flat. So let's look at that one on our calculator. So 2 minus sine theta. See how it's sort of flat on top? Okay, so we have a little bit of a flatness there. Our next one, 1 divided by 2 is less than 1. It's 1/2. So that should be an inner loop problem. So let's see what that one looks like. 1 plus 1 plus 2 cosine theta. When we graph that one, see how we have that inner loop on the inside. Now notice the inner loop, the length of the loop is 1, okay, and the length of the entire, or the diameter of the entire thing, is 1, 2, 3. That gives us an idea there. So those are the different options that we have there. So just keep those in mind. Basically remembering our rules here. if A divided by B is less than 1, then we're going to have that inner loop. If A divided by B is equal to 1, then we're going to have that, what they call the heart shape. Okay, so this one's heart shape. And again, this one's called looped or inner loop. When A divided by B is between 1 and 2, then we have a small dimple. Okay, and when A divided by B is greater than 0, we have no dimple, it's almost flat. Okay, so then we go to our rose curves. Those are our second examples. Rose curves are always to have values of your degrees that are always multiples, like 2 theta, 3 theta, 5 theta, 6 theta. All of these are 1 thetas, okay? So cosine problems, right? Cosine problems are going to be symmetric about the polar axis. 2 theta is an even number, so that means I'm actually going to have 4 petals. 2 theta for sine means I'm going to have 4 petals. The petals are each going to be of length 2. The petals are going to be of length 2. 3 theta means I'm going to have 3 petals. Sine means it's symmetric about the the pi over 2 axis. 3 petals, 5 petals, 5 petals, 12 petals. Okay, so when I go to graph those, grab a piece of graph paper really quick. So when I go to graph those, like for this one, I know I'm going to have 4 petals. It's going to be symmetric about this pole, and the petals are going to be length 2. So I'm going to have a petal here. I'm going to have a petal here. And then since I have an even number of petals, I'm going to have a petal here, and I'm going to have a petal here. So my problem is going to look like this. There's 1 petal, 2 petals, 3 petals, 4 petals. Okay, so if I wanted to check that on my calculator, I can type in 2 cosine 2 theta and graph it. And there are my 4 petals. Each of them are of length 2. It looks a little distorted because the graphs aren't to scale, but you'll notice that you're going out 2 here, you're going up 2, to the left 2, and down 2. Okay, so when I have 3 petals, like on this one, when I have 3 petals, because it's a sine problem, it's got to be symmetric about the the pi over 2. My petals are going to be 4, so I'm going to have 1, 2, 3, 4. There's my first petal. My other petals are going to be, let's see what they're going to look like. We're going to have our other petals are going to be, we could figure them out, but let's do it on our calculator. So for sine 3 theta, yeah. Okay, so there's our 4, and then we've got this length is going to be 4, and this length is going to be 4, and then this length is going to be 4. So we have down 4. Okay, there's our first one, and then our other one is going to be at our coordinates are going to be over here at probably pi over 6. Okay, and then another one over here. All right, so that's what we want to pick up on that. Our limit-gates, our last ones. Okay, so for our limit-gates, notice that these are all R squared problems. So that's what's important there. This value here is is A squared. So that means A is equal to 3 on both of these. So cosine problems mean that they're going to be symmetric about the polar axis, and sine problems mean that they're going to be symmetric about the origin. So in this case, in our first one, let me get this graph paper. In our first one, we have cosine 2 theta and A is equal to 3. So we're going to come out 3 here. We're going to come out 3 here. And our graph is going to look like this. And on the second one, we're going to go 3 this direction and 3 this direction. So 1, 2, 3. And 1, 2, 3. And our graph's going to look like this. Okay? So that's what I want you to do. So I've got some worksheets out there for you to look at. It's really important that you keep this paper handy. I expect that you will be using that to guide you along, and make sure that you're comfortable using your calculator so that you can see what the shapes look like. So what I'm wanting you to do is to be able to identify that they are an inner loop problem, a heart-shaped problem, a dimpled problem, or no dimple, and it's called a limison. And I want you to be able to identify that there are rose petal problems, that they will have 4 petals or 3 petals or 8 petals or 5 petals, and the length of each of the petals will be 5 or whatever A is in those problems. Or to be able to say that it's a lemniscate problem, and the length of A is, which is basically the diameter of the loop, and how to find A, and to determine that it's going to be symmetric about the poles or that it's symmetric about the origin. So give those problems a try and see how you do with those. And if you have any questions, just feel free to email me.